Okay, great. So yeah, welcome to this lunch and learn session. It's going to be no idea how long, probably 40 minutes to an hour. And we'll have some questions at the end if there are any. But this one is on practical PyTest, which is we have a full PyTest course as part of our sort of Gene Golding training, but this one's more sort of conceptual, and it kind of answers like why testing rather than like what is testing. So this seminar is aimed at people who know how to code. So you know how to write some code, you know how to do some things with software, uh, but you're potentially not a software developer with experience in things like version control, continuous integration. But you've heard of testing. You've been here, you've been around for long enough to know that testing's a thing. You might write some tests sometimes because everyone always says they're really useful, but maybe you're not convinced because I think it's quite hard to be convincing. The way I was convinced is that I worked in a software company where you had to write tests because that was your job, and all the sort of seniors who were teaching me how to write code would write tests as well, so I basically copied them. And now I kind of agree that it is actually useful. So part one of this is what is testing, and this is going to be very sort of general and abstract. A test is a bit of code that checks the behavior of another bit of code. Uh, there's lots of different kinds of tests. I've got a table here. The first sort of level of my table is static testing, which you could argue isn't really a kind of test, but this is something that checks code without actually running it. Like red squiggly lines in Word, that kind of thing. It just tells you in your editor you've spelled something wrong. And there's different layers of testing here. So the next one is a unit test, which tests like an individual component uh, of your software, an integration test, which tests the behavior of a few different components, and a system test, which tests sort of everything at once. There's also end-to-end tests, which test the whole system, end to end, which is slightly different from a system test in that it tests something in the same way as a user might interact with it. So, you sort of pretend to be a user logging in and see if the whole thing works. These tests might be automated, and these are going to be mostly the kind of tests I'm talking about today. But they might be manual tests. If you're writing some code for your PhD or writing something to do something, you probably want to check at some point along the way that the things work. And so you might make a little plot or a script just to check that you're generating random numbers right, or you're plotting a graph properly. And that is still a test. It's just a manual one. Unit tests are the ones we cover in the other PyTest course. So in the Gene Golding testing directory, the course directory, there's one on PyTest, and that pretty much covers unit tests exclusively. And these are also the ones that people talk about when they talk about testing. This is testing an individual component. There's an example of a unit test on the side here. The line between a unit test and an integration test is pretty fuzzy because what is an individual component versus a few components? In this example on the right, I haven't implemented like the list myself, that just comes with Python, but you could argue that is a collection of components because a list, that's not a sort of fundamental particle of code. Like a list comes with a bunch of stuff and there's a bunch of behavior in there. On some level, this is an integration test. Maybe on a more useful level, this is a unit test. So just to talk to this test here for a concrete example, the function at the top gets the mean of some numbers. This is just plain Python. There's type annotations, which might look a bit weird if you're not used to them, but this is just saying it takes a list of complex possibly numbers and returns a single complex number. And the way this works is you get the sum of the numbers divided by the length, which looks like the right implementation of a mean. And at the bottom here, we've got a test for the mean, which is called test mean. Checks if we can find the mean of some integers, and then it just runs this code here. So we've got a list of 3 numbers. We expect the mean to be 2, and we're just going to check that the expected mean, which is 2, is equal to the calculated mean, which is the one we calculate with the function on top. So that's a really simple test. It's a bit contrived, but just to be concrete, this is what I'm talking about when I say a test. Okay, so this is now going away from the sort of testing Python code stuff and more into like project management, thinking about how things get structured. Shifting left is a concept that's used in lots of industries and fields. And basically the point is do stuff earlier rather than later. For testing, check stuff earlier rather than later. So let's say you're writing some code for a publication, for example. We're in the industry generally of doing research and making publications. So if you're early on and you're having an idea and you want to change your mind, that takes a couple seconds. Then when you're designing a study, you're implementing it, you're submitting a paper and you're publishing it. at the end, by publication, if you change your mind then, it's going to take a few months. You have to ask the journal to sort of change something. It's going to take ages. And the concept here is the same in testing. If you catch things that are wrong or that want to change early in the process, then you save a lot of time early on. Like when I said about Microsoft Word has red squiggles underneath, that's a static test. If your code editor can tell you you've spelt this variable wrong and it stops your code crashing, if you can catch that early rather than late, it's going to save you some time in the long run. There's lots more to say about this kind of thing, but I'm just going to leave it there. Testing is generally it's useful because you can check stuff earlier rather than later. So to be slightly less abstract, and to link it back to the kinds of tests I talked about earlier, there's these 4 kinds of tests that I've brought up earlier. Static test, UT stands for unit test, and IT stands for integration test. These are pretty common acronyms, so I've just decided to use them here. And these check for different things. That way along the screen, because static tests are very quick and system tests are generally slower. And there's a table here telling us what these different tests check for, when they should run, and what they're triggered by, and how long they take. I'm not going to talk about the sort of details of when they run or sort of when they're triggered, but generally static tests, Microsoft Word squiggles, run as you type and they're always sort of going on in the background. Unit tests happen more quickly, more commonly whenever you sort of, for example, run git commit. And your system tests might run only when you want to sort of merge in a chunk of functionality to your main branch. So these might run on release. For example, if you're working collaboratively, these might run just when you're sort of merging the change you've been working on this week into main, for example. So to talk more concretely about these 4 kinds of tests, the static analysis stuff is stuff that your code editor does in the background and really is just for developer experience. Really, this is just to make your life less annoying. You can write all your code if you want in like Microsoft Word or Notepad or something, but that's really irritating. You probably want to write it in PyCharm or VS Code with extensions or Vim with extensions if you want, or something that can do things like auto-complete variable names, tell you if you spelt things wrong, maybe auto-format code when you save a file, stuff like that, just to make your life a bit easier. It could also check that you've formatted everything in a consistent way in Python, maybe following PEP8 conventions, just so that everything looks nice. This is really just for like developer experience. Your unit tests protect you from writing bad implementations and also from breaking existing ones. These should be really quick, and that's just so you don't have to context switch. These tests should be fast so that you don't have to sort of write some code and then run your tests and sit back and wait for a while. And then you get bored and look at your phone, and then your tests have run, and then you go back and you have to think about what you were just doing. They should be really quick so that when you run these tests, they just run and say your code failed or your code passed. Just because this is just part of the cycle of shifting left, the unit test should be quick. And by the way, it's shift left just because I've written the diagram with stuff on the left that's quicker. That's why you want to shift left towards the left quicker stuff. There's all sorts of ways to run these unit tests. You can use things like Git hooks and run things on remote servers if you want, but I won't go into details right now. The difference between unit tests and integration tests is that the integration tests are slower and prevent you from breaking bigger bits of the code, which is why I said earlier that the boundary between the two is a bit fuzzy and ill-defined. This is because, like, what does a bigger change mean? Like, what is bigger versus smaller here? The unit tests would run at each atomic change, so each sort of individual small change you make to your code. The integration test should probably run when you've completed a group of changes. For example, I might make a git commit when I've written the function signature and then a comment saying what the function does, and then I might commit at sort of every line of code if I'm sort of trying to work out an algorithm. I wouldn't run integration tests at each of those. I'd probably run an integration test when I've written the whole function, for example. And then finally, the system test is the slowest one and should test everything at once when you've sort of finished a piece of work. So let's say you sat down with your boss and said, this week I want you to, I don't know, improve the login experience of our users by adding a little bar that makes a circle while they're waiting to log in or something. When you've sort of assigned that ticket to your to-do list and you've written all the code to do it, and then you merge that into the main branch, that's probably when the system tests run. It's a sort of a bigger chunk of functionality, more often than once a week, because I think the way that people tend to work is they just write they just work on a branch by themselves and then merge it into main when they have to. That's too slow. You should be merging in sort of as quick as possible, just in general for collaborative working. But this is when your system test should run, when you're sort of releasing a new bit of software, that a new bit of functionality that other people can see. If you're just working by yourself, you should sort of keep this model in mind. So my system test might be, I've worked on a chunk of work, now my system test should run. But this is the kind of thing that you might get into anyway, just by working naturally. Your system test might just be plots, remember. Okay, this is all very abstract, so I'm going to continue by talking about more and slightly more abstract things. The testing pyramid, which is just a popular model for how to structure your tests. And it summarizes this box I've got here. You want lots of fast tests and fewer slow tests. This pyramid is showing us how many of each test we've got of each type. The bottom is static, and that's the base of our pyramid. There's lots of static tests. For example, we've got lots of red squiggles in the editor, lots of like formatting checking, lots of that kind of thing just built into a workflow. And these are fast tests that just check little like small scale changes. And then we have slightly fewer unit tests, slightly fewer integration tests, and then not very many system tests because these are slow. And why might we want that? Basically, it's because that is one of the least annoying ways to develop. System tests they force you to context switch. They're slow. You have to wait for them to run. And they're quite hard to write sometimes. You have to sort of think about all the different pathways through your code. You have to put your head into the mindset of a user potentially, depending on how you're writing your tests. Unit tests, they're much more sort of self-contained. They're easier to write in general, and they're quicker. They're just kind of nicer. So more unit tests is generally seen as better. It's not perfect though, because a unit test is also closely coupled to your implementation. So if you change a little bit of code later, let's say you're making some refactor, your code doesn't work with a certain input, you're refactoring code to work with 3D images instead of just 2D ones now, you'd have to change a bunch of unit tests if you've written unit tests already. So having lots of unit tests can be annoying because it means you have to edit all your tests as well as all your code. So there is a balance to be struck here. And that's why I've made some more diagrams as well. The first two here are relatively common. The testing pyramid is something that I think most software developers will recognize. Testing trophy is something that software developers who go on like Twitter a lot or read a lot of tech blogs will be familiar with, because there's all sorts of like arguments on Reddit and Twitter and stuff about which testing framework is the best and which model is the best for testing. The testing trophy, which is, I don't think it looks like a trophy, but that's what it's called. It's similar to the pyramid, but there's basically fewer unit tests. And this is because of what I said before. The unit tests are a little annoying because they're closely coupled to your code. So having lots of them can be a bit irritating. The testing trophy is basically lots of static tests, lots of integration tests, and then a couple of unit tests and system tests where necessary. This inverted pyramid here, this is something I've invented, and this is something that I think this is the paradigm you're in if you say I have no tests, because you don't have no tests. Your code, having no tests in code would just be writing some code and then never running it. No one does that. What happens if you don't have any tests is that you've accidentally inverted your pyramid and all the testing is happening at the end. It's possible it's not a pyramid. It's possible it's just like a stick with just system tests on the end if you literally never check anything on the way to your final product. But if you say you have sort of no testing, you might have very, very few checks early on in the process and all the checking happening at the end, when you're making your plots for the paper. And this is probably like the worst paradigm to be in. It's also maybe worth saying that there isn't a best and worst paradigm of these. How would you even measure which one you're in? Like, you can't count the number of tests and then weight by the length, or like that's not something that anyone does. So none of these are technically more valid or canonical than the other, but the more idealized ones are the pyramid and the trophy. These are more probably something to bear in mind when you're thinking about what kind of testing regime to be in. The pyramid is the purest shift left, and the inverted pyramid is the opposite of that. We've shifted all our testing right, which is probably bad. And then the testing brick, which is just, I couldn't think of a name for this. It's just a big square. And this is probably what happens if you first get really into testing and get sort of on board with testing. Like, yeah, I'm going to add unit tests everywhere. I'm going to add system tests. You end up testing everything multiple times. And this testing brick is basically me trying to say, you've tested everything equally everywhere. You're now sort of over testing. You've checked a lot of functionality in the unit tests, and you're checking the same thing in integration tests and the same thing in system tests probably. and now the tests take really long to run, and it's a bit annoying to commit because you have to wait 40 minutes for all the tests to run. There's lots of overlap between the things that are being tested, and it's not a very efficient use of time in terms of running the tests and also in terms of you writing them. But this is just something you kind of get over, I think. I think there's a transition between inverted pyramid is no testing, and then the brick is when you get sort of two into testing and write too many, and then eventually you converge onto one of the better two on top. So these are just kind of models to have in mind when you think about what are tests, how do we structure them? Okay, this is the final slide on like what is testing. People quite often say that, well, I don't see the point of testing. I don't want to write my code twice. And I think part of that is because when we show examples of, what is PyTest, what is testing, we show things like this mean example I've got on the screen, which is just ridiculous. Like no one writes a function that does that, and no one tests it either because it's so simple. So in these examples, we end up writing return sum divided by length, and then the test is calculate the sum and the length and check that it's the same. This is a really contrived example, but there is still something going on here, which is that the intention of a piece of code is different from the implementation. When I write a function that says, find me the mean of some numbers, the implementation is get the sum divided by the length, but I don't need to think about sums and length when I'm using this function. I just need to think about this function gives me the mean. So the test should test the behavior of the function, not the implementation. And that's where the sort of slight difference is between writing a good test and just writing your code twice. When you write your code, you're writing the implementation. When you write a test, you're testing the sort of intention. You're testing the behavior of the code. Okay. There was a little bit more to say to that, but we've already sort of 20 minutes in. So I'm now going to very, very briefly talk about PyTest in a nutshell, because I did promise that this is called Practical PyTest, and nothing so far has been practical. PyTest is a testing framework. There are many others. Unit test, I think, comes with Python, like lots of versions of Python. Nose test is ones that people sometimes use. But we have a whole course on this, so I'm not going to go over all the implementation details, but the gist is that we can turn a collection of functions into a test suite you can execute. And there's a bunch of features with this. You can cache things later to make your tests quicker to run multiple times. You can share common attributes between tests if you want to check some state. Sometimes I write tests that have stuff to do with images, so I just make a fixture that makes a simple black and white image. You can mark a test as like slow or flaky if it depends on random numbers. And you can do stuff like say, okay, only rerun the test that failed last time that we ran this test suite. And there's an example on top. I've cropped some stuff out of the screenshot, but basically this is saying that we had 5 tests here. In this module here, test/test unit/test maths.py, we had 5 tests, 4 of them passed, which is the green dots, and 1 of them failed. And the one that failed was called test mean empty, and we got a 0 division error. There was a division by 0. There's a nice print output. It's useful for sort of you can find the tracebacks from your tests, which is better than if you just wrote a sort of chunk of code to run yourself. Testing framework gives you nicer output, and you can also feed it into things like GitHub Actions. GitHub Actions or code coverage plugins or sort of nice status badges. It just plays nicely with like the rest of the software ecosystem that you might be using. So that's why you might want to use a testing framework. Like I said before, we have a full course on some PyTest sort of specifics. So if you sort of wanted to learn more about that, go on our course directory. There's JGI Bristol. No, it's not. It's Bristol Training, bristol-training.github.io. Maybe Rita could paste a link in the chat. That would be good. But we have a training course on PyTest, and there's lots of resources online. But in brief, it's a testing framework. So now I'm going to do a very, very brief live example just to illustrate the mechanics of testing. I have to bring up my terminal here. Let me know if you can't see this because I don't know if I'm sharing screen or window. But I'm just going to, so I'm in an empty directory here. And I need to clone the right thing. So, I mean, this repo is available online. I'm just cloning it to prove it's all sort of real and there's no funny business going on. So we're in this directory here. There's a bunch of files here. And this is the example I'm going to use for testing stuff. I'm just going to quickly show you what it would look like to run some tests. I'm using UV to manage my Python environment here, just because it's extremely convenient. So I'm going to run UV run PyTest. So all this does is say run PyTest with the the UV Python environment, which is defined by this PyProject file here. We also have a short course on using UV for package management, which is quite good. And I'm going to tell it which tests to run. There's tests in the test directory, and then test unit is where I keep my unit tests. PyTest automatically discovers tests that have test in the front. So because I've got tests here and then tests unit, it's going to run everything in this directory. And this is the error we saw earlier. I'm just going to make my screen a bit bigger. So what we saw earlier was these 4 green dots and the red F, and the red F is this failed test here. So my unit test ran in half a second, which is, I think actually relatively slow for a unit test, but it's pretty much instant. One of my tests has failed, but 4 have passed. Okay, so just to quickly look at what's actually going on here, I'm going to clear the terminal, and then my code is in the source directory. This is all that's in my maths module. It's just a function that takes the mean. I've shown this before. This is a function that just literally takes the mean of a list of numbers. It looks like it does the right thing. The sum divided by length. Cool, that's what the mean is. And then I'm also going to show you the tests file. And I'm going to open that in Vim. Test unit. This is my tests file. There's lots of tests here. And in my notes, it says talk through all of them. I'm not going to because they're relatively boring. The first one tests if I can find the mean of some integers, mean of some complex numbers, mean of some floats, mean of some negative numbers. That's kind of like mainline testing. That's the kind of stuff I want to test if my function works with ints, negative numbers stuff. I'm just thinking about edge cases, which is one of the useful things that testing makes you do. It forces you to think about edge cases. And this last one here is one that's failing. Maybe for some reason, if I'm doing some data analysis, I might want the mean of an empty list to evaluate to 0, just so it doesn't break my stats or so I don't get not a number or something like that. This isn't what my test does, though. What my function does. What my function does is if the list is empty, it finds the sum of the list, which is 0, and it also finds the length, which is 0. And then it calculates 0 divided by 0, which gives you a 0 division error. So maybe I change my mind. I think, oh, actually, perhaps the right behavior would be to raise a 0 division error if I try to take the mean of an empty list, for example. So I'm going to change my test to test for this behavior. So I'm going to use with PyTest.raises, which is something we talk about in the PyTest course. With PyTest raise 0 division error, I'm just going to calculate the mean. So now when I run this again, all the tests pass because now the behavior that the function has matches the ones in my test suite. And this is kind of useful. This is still a bit contrived, but the point of this is that when I have my testing suite, that defines my expected behavior. So if I write in my testing suite, test that the mean of an empty list is 0, a failure tells me that the behavior in my head doesn't match in the implementation. And equally, now that I've changed this to raise a 0 division error, if I'm sort of new to this code base, I can go to the tests, look at what it does, and I can see here that, well, look, the person who wrote these tests, their intention was that the mean function should raise an error if the list is empty, which is information that's otherwise implicit. And then you could probably, you do something like put it in the doc string of the mean function. You might explicitly raise an error or something like that. But the point of this is to basically to say that having this test here has forced me to think about my implementation more than I would have done otherwise. Because otherwise, the mean is just the sum divided by the length. Just write that down and then you're done. You don't think about it again. And then maybe it crashes in future when there's an empty list. But having the tests makes you catch that crash a bit earlier. Okay, boring. So that's a contrived example again of tests. So what are the benefits of this? We're going to get a bit, we're going to go back to being a bit sort of philosophical and vague maybe. How do we define correctness, because code doesn't work with all inputs. If I do my mean function I just showed you, if I gave it a number that was too big for my laptop to hold in memory, it would crash. But I don't test for that because I don't expect that to happen. The code doesn't work with all inputs because that would be ridiculous. It only works with sensible ones. And you can test, some of these sensible inputs, and you can also test some non-sensible ones. I don't know if any of you have heard, there's a joke about software tester and engineer. A software tester walks into a bar and orders a beer, orders 2 beers, orders infinity beers, orders -1 beers, and the test will pass. Then the first user walks into the bar, asks where the bathroom is, and the bar bursts into flames. Like you can't reasonably think of every possible input to your code, but the point of testing is to sort of think about what a user might do, put yourself in their shoes a bit, and just try and check for things before the bar bursts into flames, before there's a crash in production or something. One of the benefits of testing is that it forces your code to be testable, which is like a bit of a tautology, but it means some concrete things. For example, it makes it clear in your head what the code does. It forces you to think about edge cases, like I just showed with there's 0 division error in the mean function. Good tests force your error messages to be useful. If your code raises value error in lots of places, you might find that your test is constantly checking for value error, and then you might think, well, this is weird. This check isn't actually checking all that much. This is just checking, is there a generic error? You might then write some custom exceptions to raise things like, create things like image not found error, or like more specific errors that should be tested for. And you can think, well, you can get these benefits without testing, but you won't. Unless you've written tests before, it's extremely hard to put yourself in the mindset of writing code that is testable. So going through the process of like writing tests for code makes yourself write code that's more testable, which you can then sort of write a bit fewer tests and try and keep that skill, try and keep the sort of code testable. But it is a skill that kind of atrophies, so it's useful to just keep writing tests for your code to make sure your code remains testable. It's one of those things where you can force yourself to do it, but you sort of won't. And the reason that you have these systems is because, like, as a human, we're like we're fallible. We will make some mistakes and we won't do everything perfectly. So then having a system where I need to write tests makes you write your code more testably without having to sort of force yourself to, just through like mental willpower. Okay, there's a stupid meme on this slide, but we thought it was a bit funny. You don't need to test everything. If you're a data scientist, you might have a pipeline that reads in some data from a CSV, does some like one-off data cleaning, chains together some library functions to do like a linear regression, and then plots that linear regression line on a graph. You probably don't need to test any of that because having the graph at the end that looks right, that is the test. Writing some tests for code that you need to think through, though, that becomes more useful. If you find yourself sitting at the keyboard and thinking, okay, what do I do now? And then I need the pixels on the edge are this color, so I need to, like, if you find yourself thinking about stuff, you're having to think about things algorithmically, the tests help you sort of nail down what your code is doing. It helps you define correctness, and it gives you a bit more confidence that you're doing something right. I mean, like I've said, you might not need additional tests if the code is good enough, if it gives you the right output. In that linear regression example, if the linear regression looks right, then that's okay. The code is like correct because the plot looks correct, and that's how we are going to define correct for this bit of code. But otherwise, you might not write any tests. You might not write any tests until the point you're changing stuff. Let's say you did a linear regression and there's no test, but now you want to change it to fit a spline to the code. Well, now you might want to add a test just checking if the regression works with the straight line. Change the code to fit a spline and then check that it still works with the straight line, because the straight line is an example of a spline, but just a simple one. Just to check that you haven't sort of broken backwards compatibility, just to check that your new code doesn't break the old behavior. So this meme here, I'm just going to explain it. On the left, we have a guy who's on this left-hand side of the IQ score bell curve. He has no tests. And the guy on the sort of high IQ score also doesn't have any tests. I've put brackets yet. And the guy in the middle is talking about all sorts of stuff because he's over-testing. There's all sorts of problems with this meme. The IQ model is not very good. It's not going to be a bell curve here. It's impossible to know like who's to the right of you. So I wouldn't take the meme too seriously. I just thought it was funny. But there's such a thing as over-testing. And the answer to when to test isn't all the time. It's like sometimes. It's when it's useful. And you get a feeling for when it's useful by just kind of trying to write some tests for your code. Okay, this slide is really short, and I've already talked about it. I've got 3 benefits of testing, and they're going to be in 3 slides that I'm going to rattle through pretty quickly. Number 1 is making sure your code works. this is the most obvious benefit. It guarantees functionality, so it makes sure your code works, and it prevents regressions, which means it makes sure you haven't broken your code. So let's say I was going to write a test for my mean function. If I then change its behavior to use like NumPy arrays instead of lists, having a test would just make sure that I haven't broken the old behavior when I change it a bit. Another example might be if I then get more data and then one of my functions is really, really slow because there's now more data. I optimize the function to make it faster. Having a test is just a really good idea just to make sure I haven't broken all the behavior. Because I think if you didn't have a sort of unit test or integration test, the way you check if your optimized code was still working would be just to run the whole pipeline. And that's just a system test. So why not shift it left and make it a unit test? Okay, number 2. This is, I think, the most underrated benefit. This only really applies for like automated tests. And you can automate your tests for free if you're hosting your code on GitHub. GitHub Actions is free, really easy to set up because you just Google it or use ChatGPT to write you the right file. You just need to write a config file. It tells GitHub, whenever I push my code, run this set of tests, and it will just do it for free. The like hosting's free, it just works. It gives you a nice little status badge thing if you go to the right bit of GitHub. And there's a lot of good benefits to this, I think. If you have some automated tests that run somewhere, you know that there must be some well-specified environment setup script. There must be something that is running to check if it works that you can then do yourself on your laptop. You know that the right environment is getting checked properly because it's also running some code. So you know that the environment and the code work together. And you've also got some free instructions on how to set up the project. So you can go to the test and see that testing steps are set up a virtual environment, activate it here, install the right packages, run this script. You can just copy that on your laptop. And then you've sort of removed a lot of the mystery of it working on a new project. Because the first thing that happens when you work on a new project or sort of work with someone else is that you clone the code and then you think, okay, does this just work? Or do I have to be on the right person's Mac with the right folders installed in the right places and the right version of Python and everything? You can check, does this code just work by just running some tests? And that's, I think, the most underrated benefit. So even if your tests are bad, even if there's just one test that just checks, does my mean calculate the mean of like 1 and 2 properly? Even just having a bad test gives new users a free recipe for setting up the environment for your package, which I think is a really underrated benefit because that is the hardest thing when coming onto a new project. And this is the third benefit, which is the biggest in a sense because there's the most possible stuff you could do with it, but also the smallest in a practical sense in that you probably won't need to do this. Once you've got tests set up, you can feed them into other things. Like you can have a badge in your README on GitHub saying, look, my test status is green and my tests are all passing. You can have metrics saying like the code coverage is 80%, the branch coverage is some other number. You can say in your report or like grant application, all the software will be unit tested and will have 80% branch coverage because maybe in a grant application, you've said that you do this and it made the people reviewing it more confident in your ability to write code. And now you actually have to do it. So you can do all sorts of stuff to make it look like you're better at coding by doing this testing stuff. And this isn't a trick, by the way. You're not tricking people. This is actually just being better at coding, is being able to fluently do this kind of thing. This isn't always useful. It's very specific to the project. Maybe you don't want to spend all the time setting the stuff up. If your research output is going to be a software package, maybe you do. If it's going to be a paper where you just have some like bar charts, maybe it's not useful. You might not get this far, so you might not need to do all these badges and sort of code coverage and testing on different environments and like all sorts of stuff. But it's good to know that it's possible, I think, in a sort of general sense. Okay, and this is pretty much the last part of the presentation, other than the conclusions. It's an actual example of writing a test. This is something that I implemented for a project. It's a couple of months ago at this point. But this was for an image processing pipeline. We had some image and it had an object in it. And we wanted to find equally spaced points around the edge of the object. So there's an image and it's got, there's some structure and stuff there. So there's a bit of stuff going on, but it's not too difficult. So as a human, you can do this quite easily. You just sort of see the object and write dots around the edge. But the challenge here is going to be to make the computer do it. So there's a couple steps here. So the pseudocode's at the bottom of the page here. I've said find edge points is my function name. It's going to take a pixel array. So this is my image is an array of pixels. and it's also going to take the number of points I'm putting into it. So the edges I want to find first. So there's some function which is find edge pixels. Then we're going to make a contour out of them. So I found the pixels on the edge, and then I want to join them together just with a line. This is what you do if you were doing it on paper. And then I'd find even points around that line. And so these are all the steps we can do in our head. This is probably roughly what you do if you were doing it on paper. But here we just want to sort of formalize it and write it into code. So I'm going to share my testing repo again. So if I just clear my screen. First, I'm going to show you the code that does the edge finding. So there's a little bit of stuff going on here. It's not hugely complicated, but it's also not hugely simple. Reiterate, this is the code that does the edge finding. This isn't the test. I've got a docstring in my module here. There's only one thing it does, so because this isn't my actual code, this is just like a semi-contrived example. I import some stuff to use them, and this is my function. It's going to find the points around an edge, so I've called it points around edge, and the inputs are a binary image and the number of points we want around the edge. There's some information here. This performs a slight smoothing as the contour, but like we don't need to worry about that for now. This is just some information that I wrote basically for myself to be aware of. And then the parameters. So the input is the binary image, the number of points, and the output is the x and y coordinates of the points. So it's going to return two arrays, one of x and one of y. I need to worry about and read if I'm using this code. This implementation here, this is the sort of internal guts of the function. I don't care about that. In much the same way as when you're talking about anything, if you're talking to a person, you don't care about their sort of internal contents. You care about the sort of external, who they are, how they behave, that kind of thing. This is the implementation. This is the like behavior intention. This is what I said earlier about how you test the behavior of a function. You don't test its implementation. I'm going to take us through the implementation anyway, though, just so we're clear about what's going on. This is the same as the example I showed in the pseudocode. So first thing we do is find the edges of the image. I'll call this contour points. And then I've joined them together with this sort of smooth line here using the shapely.linear ring. It doesn't matter about the sort of what this does, the implementation, but basically the point of me showing this is what we're doing. We're finding the point pixels on the edge, we're drawing a smooth line around them, and then we're finding points that are equally spaced on that smooth line. So there's stuff here, and then we're just going to make two lists of x and y points and then turn them into arrays to return the right thing that the function promised. This is probably an example of an integration test because there's quite a lot of bits going on here. I'd say a unit test would be testing these things in isolation, but I don't think we need to test those because these just come from libraries. I trust that the skimage measure library has the find contours function properly implemented. I trust that the linear ring works from Shapely. I trust that numpy.linspace works, and this interpolate point function. I trust these things, so I don't need to unit test them. What I will test is the combination of them together, which is the integration test. I'm testing that everything works together. And this isn't to check the implementations of these things individually. This is just to check that I've stuck them together in the right way. Okay, so I've shown you the implementation of the edge finding function. Now I'm going to show you the test. And this test is much simpler than the mean test, by the way. Test integration, test edge finding. So, sorry. So I'll just type this in at the top here, just so we're all following. And this is the contents of my testing file. I'm going to import NumPy because I'm going to use it. And I'm going to import the function that I'm testing. And all this function does is check that we can get the expected edge points around a diamond shape. So all I'm going to do here is make I've called it square, but this is just a two-dimensional array. And you can see there's ones here in the middle, and there, and there, there, and there. So it's kind of like a diamond shape here. I'm not brave enough to try and annotate on the screen, but you can see there's a diamond in the middle. And then I've just gone through on paper, on a separate piece of paper on my desk, and just said, okay, if I wanted to find 10 points around this diamond, where would they be? And it's quite simple. We use this the origin is at one of the the vertices at the top left or maybe bottom left here. But we can work out which the expected x and y points are. We can say, okay, if I had 10 points, there'd be one here, 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 here. 10 points around the edge of the diamond, and then just check that my function that I've written gives me the same points back. And I found this a really useful test when I was actually writing this code, because there's all sorts of things that I've kind of skated over that might have become clear as I was talking about it. Does the origin start from the top left or the bottom left? Does it go from sort of here that way? Is x across or is x down? Like, there's a lot of implicit assumptions here that if you just wrote the implementation, you'd really just be hoping that it worked. And then if you ran your whole pipeline and then the bits where it found the points around your objects, if that didn't work, you wouldn't really be sure if that was because you read the images in wrong, or you've maybe decoded them wrong, or you found the edge points wrong, or you've plotted it wrong. Like, it would be, there's lots of stuff going on. So having this test to check that you can, just even a simple shape like this diamond, because that's nowhere near as complicated as the actual shapes I was trying to find the edges around. But this sort of tethers the code to a real life example. So what I actually did was I wrote this test first, and then I worked out where the point should be, and then I wrote the implementation of the code just to make sure that my implementation was kind of tethered to a concrete example of something in the real world. You can imagine that like this test is very simple, and if I wanted to sort of properly test something to make sure it was good enough to release, I'd have lots of tests for different shapes with holes in it, 2 disconnected shapes on the same image. There's all sorts of possibilities, but the reason I wrote this test and the reason I wanted to show it was because this is real. This is something that actually helped me with writing code. If I hadn't had this test, it would have been really difficult to keep all the sort of assumptions and the stuff my code is meant to be doing in my head. And I mean, this test also runs quite quickly. So let's see what happens if I run UV run PyTest test integration. So there's only one test in here. And the test runs in less than 1/3 of a second. So this is what I mean by sort of shifting left. I've taken the time to write the test, but now if I change the edge finding code to use a different algorithm or do something else, I can just check it works by just doing that. And that can run on GitHub Actions, that can run sort of anywhere. It's taking 1/10 of a second to run. I could have lots of these tests and I'd be checking lots and lots of stuff. And it makes it a lot easier to change things. If you don't have any tests and then you change something and you have to say, okay, has it broken the edge finding? Has it broken the plotting? Has it broken my algorithm for filling in the holes in the image? Like, there's loads of different things you'd have to check manually. And if you can just do this and then check all of them, it doesn't check them all perfectly, but it checks them all to some extent. It makes it a lot nicer to develop your code, and it makes you much more confident in changing your code as well. Because something that happens after a long project is that you get a bit scared of changing things because who knows what will break. Well, having a test makes that a bit less scary. Okay, I think that's probably enough for that. I've written some more stuff down, but it's all pretty much me repeating myself. Finally, I've got some take-home messages because we're sort of nearly at the end of the session, and a lot of this has been very abstract about shifting left and testing pyramids and stuff. Some concrete recommendations for stuff to do. Static analysis is the quickest win of these kinds of testing. In the testing pyramid, it's the bottom. In the testing trophy, it's the biggest one. And in the bad example of the testing inverted triangle, it was the smallest one because that's bad. Static analysis is the best way to just introduce some concreteness to your developing workflow. The stuff I use in Python is there's rough, which does general static analysis on things. Rough does a lot of different stuff. Black is a good formatter, so it's called something like the opinionated Python formatter. When I save a file in VS Code in Python, it just formats it for me with black, and then I don't have to worry about writing stuff properly. I can just write horrible long lines of code with like nested list comprehensions and like long variable names, and don't worry about the line length or anything, because when I save it, it'll just format it into a nice looking way. Pylint as well is something that you can get a bit obsessed over. It gives you a score out of 10, which is fun. And it just checks for things like, have you shadowed a variable name? Have you forgotten to define something? Have you, common developer pitfalls? You forgot a bracket. You've closed a parentheses with a brace. Just stuff. It just checks for things like that. And it's basically like having a very simple code review just run instantly. And then MyPy is for checking typing, which if you don't know about Python types, they're great. But that would be a whole new course to talk about, which I really don't want to do. But MyPy just formally checks your typing. The recommendation for writing proper tests that aren't just static analysis, tests that actually run your code, would be to start by writing a unit test or an integration test. If you've already got a script that is, it checks your code by making something, see if you can turn that into a system test. If that's easier for you, then that'd be good. But if you have nothing, I'd start by writing a unit test or integration test, similar to my sort of point finding one. I'd write a test for something sort of algorithmic, where you've sort of had to think about lines or write on a whiteboard or sort of think through it. Something that's hard to reason about, similar, or something that's previously been broken. For another project, I had to find I think it's called the time series skill. So there's two time series, and there's some number that you get by comparing the two. So you do something like take the variance of the difference divided by the variance of one of them. It's not very difficult. It's just a single line calculation, but I implemented it wrong before. And when I realized that, I wrote a test for it, ran the test, it failed, which I knew because I knew the code was broken. And then I fixed it. I think I was finding the variance of the sum instead of the difference or something. But if this code was broken before, which tells me, okay, this is somewhere I've made a mistake before, I don't want that happening again, so I'll write a test for it. So that's also a good place to start adding tests. Here's an optional thing, but this is the thing I said was the biggest benefit. If you have a GitHub Actions, if you're saving your stuff on GitHub, you have access to GitHub Actions for free. You can make a GitHub Action script to run it easily on push. I haven't gone into how this works, but it's easy. You Google it or you ask ChatGPT, give me a config file to run this script on push, and it will just do it because it's quite simple. Basically, you write a config file that tells GitHub which tests to run when. If you like it, you can go further by having sort of automated test every push. You can have a test status badge in your README. You can generate a code coverage report, and it sort of highlights your lines of code in green if they're tested and red if they're not. You can make a dashboard that shows your project status. So you could have a screen in your office that has a big red button on it if your tests have failed overnight or something. But that's going a bit far. That's doing all sorts of lots of extra tests. I think part of the process is a necessary overcorrection. I talked about the testing brick earlier, which is just having lots of tests at every layer. That's if you're writing too many tests everywhere. But I think that might be necessary for getting a good feeling of what is useful. And writing too many tests at first, it's quite fun because then you feel like you're being productive and you're being sort of a proper software developer. And then it gets annoying because you have to change them all the time whenever you change the code, and they take a long time to run. So eventually pare them down, and then you end up with your nice testing pyramid or trophy, or you've ended up learning what's useful. So yeah, my concrete recommendation there would be start with a unit test or integration test. But if you have something that already checks functionality by plotting a graph, you're pretty much there already. Just turn that into an automatic test. So then finally, the conclusions. There's a couple different kinds of tests. There's the fast, small tests that have the quickest turnaround of finding bugs. But these are also most closely coupled to your code. So if your code changes, these tests will have to change more, and that might be irritating. Having even simple tests give you some useful guarantees in that it tells you how to set your environment up. It guarantees that even basic things can just run. It checks some basic functionality of bits of your code. And then I guess the sort of final motivating part of this is that knowing about tests is the reason this presentation hasn't been just lines of code and showing stuff how to run is because that's training on how to type in lines of code, which you can just Google. I can't tell you what will be useful for your project, but there's all sorts of this kind of more abstract stuff, which is part of the transition from just writing lines of code because they're in the right course to developing software, which is where you have to be if you sort of want to write code to do anything useful. And knowing about testing is one of the bricks for that. And I think testing is an especially useful brick because it sort of encompasses all sorts of things like code design. So your code has to be modular and scalable to be tested properly. It tells you about environment setups. It's telling you about sort of collaborative working on GitHub and branches and stuff. So testing is it's a relatively advanced topic because there's lots of things to it, which is why this sort of presentation was mostly about process diagrams and things. But it's really important, I think, because it's part of the transition from just writing out lines of code to developing proper pieces of software that people can trust. So that's the presentation. We've got about 5 minutes if there's any questions, but if not, thanks everyone for coming. And yeah, feel free to unmute and ask questions or to type in the chat.